Hello, my name is Gianluca Ruocco, and this summer I got to participate in Cornell University's CLASSE 2025 REU program. Now, CLASSE stands for Cornell Laboratory for Accelerator-Based Sciences and Education, and the main focus of CLASSE is to make use of X-rays produced by high-energy electrons to advance accelerator technology. Cornell has a particle accelerator called CSER, the Cornell Electron Storage Ring, that runs underneath the alumni field, which is very cool and the focus of the program. But anyways, this summer I was placed under the mentorship of both Sadie and Liana and into the SRF cavity group at Newman Lab. And you may be wondering, what are SRF cavities and why do you need a whole group of people working on it? Well, SRF cavities are the parts of the particle accelerator that actually accelerate the particles. SRF cavities are superconducting radio frequency cavities, and they look like this. They're made of superconducting material, which is material when exposed to a weak external magnetic field and at low temperatures exhibit zero resistance, which is crazy. Once you inject the SRF cavities with electromagnetic RF waves, they resonate internally, creating an alternating electric field which accelerates the particle inside of them. Now, the problem with this is that niobium, one of the main materials that they use for SRF cavities, oxidizes, which does create resistance and reduce the efficiency of the cavity. In order to get rid of this, my mentors decided to layer the cavity with gold, which does not oxidize and is also a normal conductor that superconducts when placed on the surface of its superconductor. This is where my project comes in which it is the microscopic investigation of gold capping layers for niobium SRF cavities, which is a lot of words for essentially looking at gold layers in microscopes, which is what I've been doing all summer. There are a couple ways to plate the niobium samples I was using with gold, and the two ways that I was looking into were electroplating, which is where you dip the niobium into gold plating solution and then electrify it, and the other is electron beam evaporation deposition, where you place the niobium sample over a crucible filled with gold, and then you fire electrons at the gold until they vaporize and condense over the sample. Once you use either technique, you get niobium samples that you can look at underneath a microscope and have gold on them. Now I got to work with two microscopes, the first being a laser scanning confocal microscope, which looks like this. And basically how it works is it fires a laser at the surface of the gold-layered niobium samples, which then sends back signals that can be read into an image to profile the sample. To get an understanding of how detailed these images are, here are some images I took of my very human hair. And the detail is pretty amazing, and it is pretty cool. Here are some more pictures that I took of the samples with this method. The second microscope I got to use, and arguably the cooler one, is a field emission scanning electron microscope, or FESEM for short, and here's what it looks like. Now let me tell you, this machine is amazing. How it works is you place your samples into a vacuum chamber, which has a really cool procedure that's playing right now. But basically, once it's in there, you fire an electron beam at it, which bounces off the atoms, ejecting lower shell electrons that give off signals. These signals correlate to specific elements. Here are some cool images I got from that. Overall, my experience at Cornell has been amazing. From its scenic views to its wonderful nature, it's really an amazing place. It has been an absolute blast coming here and participating in this research program, and I got to learn a lot about accelerator physics and do even more stuff. A big thank you to my mentors Sadie Seddon-Stetler and Liana Spani for their support. Thank you to Dr. Matthias Leap for the program, which was also supported by the Department of Energy. Thank you so much and have a wonderful day.